Hello and welcome students of AP Chemistry. This is going to be the first lecture in our Unit 1 about atomic structures and properties. And this section is about moles and molar mass. And if you're taking AP Chemistry, you should know all of this already. But, just in case you need a refresher, let's go over the basics because this is going to be a fundamental concept in all of chemistry. Our learning objective here is to be able to calculate quantities of a substance or its relative number of particles using dimensional analysis and the mole concept. And if you are unfamiliar with dimensional analysis or need a refresher on it, I'd recommend that you go to the resources folder and check out the math section there because I've linked a couple videos about math that are going to be important to your understanding in this class. And feel free to reach out to me if you need some support with it. Now, a mole is one of the most important units in chemistry. And it's a unit much like grams or meters or liters or something like that, but it is also a unit of counting. And a mole is equal to exactly 6.022 times 10 to the 23 or 602 sextillion of something. It's kind of like saying you have a dozen of donuts, but this time you have a mole of atoms, and the number is incredibly massive. I linked a video here about the history and magnitude of a mole, and I recommend that you pause this video and go watch that one real quick. It's a TED Ed video, and has fun animations and has a good explanation of it. But let's go into the more specifics of how it's used in chemistry. Now, in science, most units are based off of some sort of standard measurement. Like I think grams and milliliters are sort of based around like water and like quantities of water. For the mole, it's based around quantities of carbon, specifically the carbon-12 isotope. And a quick reminder of what that means. Isotopes are when you have atoms that have different masses because they have different amounts of neutrons. Remember that the number of protons in an atom is sort of its defining feature. Carbon has 6 protons and only carbon has 6 protons. But that was sort of tangential. Let's get back to the point here. Now, the mole is based around the amount of particles that are in exactly 12 grams of the isotope carbon-12, which is the most common form of carbon. And this is significant because an atom of carbon also has a mass of 12 AMU. AMU stands for atomic mass units, and 1 AMU is roughly the mass of a single proton or neutron. So it's a mass unit that's sort of connected to the small building blocks that make up the atom itself. This is also relevant to carbon-12 because it has 6 protons and 6 neutrons. So in this case, we're attaching a number in grams, something that we can easily measure, to an equivalent number of really, really, really small particles. And this gives us the relationship of 12 grams per 1 mole of carbon. And we call this relationship the molar mass. And the units it's usually represented in are grams per mole, so grams over mole, like we can see here. And coincidentally, because we based that off of the mass of carbon in AMU, the molar mass will also be equal to the mass of the substance in atomic mass units. And the point of all of this is it gives us a very convenient method to convert between the mass in grams of a substance and the moles of particles that are in it using dimensional analysis or proportional reasoning. Let's look at some examples real quick. So say we had 123 grams of carbon, and we wanted to know how many moles this was. Like you could look at a scale and see 123 grams of carbon, but without knowing the relationship between the amount of substance and how much that substance weighs, we don't really have a good idea of how many particles of carbon are in that mass. But we do know that there is a relationship between 1 mole of carbon and 12 grams. And you'll see here that in this example, I took that ratio that we showed in the last slide and I flipped it upside down. Before we had 12 grams per 1 mole, and here we have 1 mole per 12 grams. It means the exact same thing. Kind of the convenient thing about using dimensional analysis is any sort of ratio or conversion factor we can either use right side up or flip upside down depending on what kind of conversion that we're doing. So in this exact example, we have 123 grams of carbon, we know that we have 1 mole per every 12 grams. And using dimensional analysis rules, we are going to be canceling out units of grams because they're dividing by themselves and becoming 1. And now we have units of moles left over. And then we do the arithmetic part. So we have 123 divided by 12. And that'll give us a final answer of 10.3 moles of carbon. And you'll also notice that the original number, 123, this was 3 significant figures. In our answer, we will also be representing in 3 significant figures. Once again, please check the math resources folder if you need a reference about how to use proper significant figures. One other little point about sig figs before we move on to the next example is that you might notice that, well, there's only 1 significant figure in 1 mole and 2 in 12 grams. Significant figures do not really apply to ratios or conversion factors, only measured values. So the fact that we have 12 grams per mole here, those figures are not considered to be significant and aren't going to affect the accuracy of our answer. So 1, 2, 3, we have 3 significant figures in this answer, or in this measurement, so therefore we should have 3 significant figures in our answer. All right, let's look at this other example. So this was an example of using an amount of grams in carbon and figuring out how many moles of particles that is. Now, sometimes we might know how many moles of particles are going to be produced in a reaction, say through stoichiometry, which we'll get to much later. But say we have 0.456 moles of carbon, and we wanted to know what kind of mass that we'd expect. Say we did some calculations and we knew this is how many moles of carbon we needed, but we needed to know how much mass to measure out. We can sort of use the same process here, but instead we have 12 grams on top and 1 mole on bottom, so that moles can cancel out and become 1, and then we have units of grams left over. And then we just do 0.456 times 12, and that'll give us 5.47 grams of carbon. Once again, we had 3 significant figures in our measurement, therefore we should have 3 significant figures in our answer. So say we wanted to get the molar mass of something more complex than a single atom. Well, it's pretty simple. All you have to do is just sum up the mass of all of the atoms involved in the substance and make sure to multiply them by the quantity of those atoms in the substance. So for example, let's try to calculate the molar mass of calcium nitrate, which has the formula CaNO3 So we have 2 nitrates attached to a single calcium atom. So we're going to go through each of the atoms involved in this compound. So we have calcium, and we have 1 of them per unit of the compound. We can look at the periodic table and find that calcium has a mass of 40.078 grams per mole. Often if you're given masses on the periodic table, unless it rounds down to 16, like oxygen, where it's usually 15.99, you're going to want to use as many significant figures as possible, or as many digits as possible that are given on the periodic table to make sure that you're getting the most accurate mass possible. So for here we have calcium, which is 40.078 grams per mole, and we have 1 of them, so we're just going to leave that alone. And then we have nitrogen, which has a mass of 14.01 grams per mole, but this time we're going to multiply that by 2, because if you notice here, the nitrate part of the compound is in parentheses, and there's a 2 outside the parentheses, which means that 2 affects everything on the inside of it. So per unit of this substance, there is 2 nitrogens. So we're going to take our nitrogen mass, multiply that by 2, so we end up with 28.02 grams per mole. Now let's look at our oxygen. Since we have 3 oxygens per nitrate and 2 nitrates per full unit, that means we have 2 times 3, that's 6 oxygens. So now we're going to take our mass of oxygen, which was 16 grams per mole, and multiply that by 6 to get 96 grams per mole. And then to get the molar mass of the compound as a whole, we're just going to add all of these values together. So we're going to add our 40.078 plus our 28.02 plus our 96 and get a total mass of 164.1 grams per mole. And I don't really care about significant figures in this case because we're not making a measurement. We're just looking at the ratio between mass and moles for a specific substance. But like I said before, you're going to want to get as many values in your ratio as possible to get more accurate calculations later. Another important thing that's associated with moles is the concept of molarity, which is the it's sort of a unit of measurement that represents concentration. And much like the molar mass, it's always telling us how much of something per amount of something. And in this case, we're looking at the moles of a solute dissolved in a solvent to make a solution. So these words can be kind of confusing because they all sort of sound the same. But say you had some salts and you put it in water. The salts would be your solute. The water would be your solvent. That's the thing dissolving the solute. And then the leftover thing that you would get, the salt water, would be your solution. So when we're calculating the molarity of something, we're trying to calculate how many moles of the thing were dissolved in the solution as a whole. And the more things there are dissolved, the higher concentration of that thing. So molarity is usually represented as capital M, and that usually stands for moles of the solute per liters of the solution. And note that it's per liters of the solution, not per liters of the solvent. Normally, the amount of solution and the amount of solvent are going to be roughly the same, but just make sure that you're calculating the total volume of the solution when you're making these calculations. So say we wanted to know what the molarity of a 400 milliliter solution containing 25.0 grams of sodium chloride would be. Well, if you look at what molarity is, it's moles of solute per liter. So we can't just use this 25 grams right out the bat. We need to convert this to moles first. And you also notice that we have 400 milliliters when we actually want liters of solution. So we're going to have to do a conversion there as well. So let's go through it. First off, let's take our 25 grams of sodium chloride and do a mole conversion. So we're going to find the molar mass of sodium chloride, which is 1 mole per 58.44 grams, or 58.44 grams per 1 mole. I have it flipped here so that grams can cancel out. And I calculated this by doing the same thing I did 2 slides ago, where I got the mass of sodium and the mass of chloride, and I added them together. So if I divide 25 by 58.44, I'll end up with 0.4278 moles of sodium chloride. One thing you'll notice here, just based off of sig fig rules, is I had 3 sig figs here, but I used 4 here, and that's totally okay because I'm not at the final answer yet. Generally, when you're doing math that involves measurements, in the in-between steps, you're going to want to carry as many digits as is convenient. Try to do at least one more significant figure than you need in your final answer so that you're not rounding too much. So the next part of it, since we need to know the moles per liter, we need to take our 400 milliliters and turn that into liters. So this is an important ratio that you're going to have to consider very often in chemistry, but the relationship between 1 liter and milliliters is 1 per 1,000. You might think about milliliters or just milli as a prefix in general being related to like a millennium. It usually means 1,000 of something. So there are 1,000 milliliters in a single liter. So in order to calculate how many liters we have, we're going to take 400, multiply it by 1 liter over 1,000 milliliters. Milliliters cancel out, we get units of liters, and we have 0.4000 liters. It's a little bit redundant that I have all of these zeros, but I'm just trying to be careful about the significant figures. Now, finally, to get the molarity, or the concentration of the solution, I'm going to take the moles, which I calculated over here, and then divide that by the liters, which I calculated over here. So 0.4278 moles divided by 0.4000 liters will end up with 1.07 molarity, or 1.07 molar, it's usually referred to. And you'll notice that I have 3 significant figures here to match the fact that I had 3 significant figures in this measurement. You also might be wondering that, well, I have 4 significant figures in this measurement. If I'm using multiple measurements to derive a single value, I'm always going to take the one that has the least amount of significant figures and use that as my reference point to how many significant figures my final answer should have. So that's why I have 1, 2, 3 here. And that is all for this section. Now go check out 1.2.